Thank you very much. So yeah, this talk is going to be about runtime optimization of C++ code. So it's going to be quite different from everything you've seen so far. So instead of trying to generate clever compilers for functional programming languages, this time we try to see what functional programming features we can integrate into a C++ compiler. So I'll start. I'll start off by saying how this is relevant to this community and what aspects of functional programming I'm using in this work, and how we can make runtime optimization, automatic parallelization, and dynamic retargeting from these properties. And I'll talk briefly about evaluation. So functional programming in C++, you'll find a lot of documentation on that. People have been trying that for ages using template system, using notion of stream, pure functions, and so on. That's not going to be the subject of the talk today. We're just interested in mainly two aspects of functional programming. One is high-order functions, which have a very well specified behavior, which I call algorithmic skeletons. So in Haskell, you have your map, your zip with, you reduce. And in C++, I have the same thing with for each, transform, accumulate, and so on. And we're looking at the usage of this in conjunction with Lambda functions. So Lambda functions is a new feature of modern C++, of C++ 11. And it brings new concepts to the language, like immutable data, strong ownership, and an ability to track the side effects statically. So I'll come back to these later on. So to show you what kind of example, what kind of application we're looking for here, and I'll briefly talk about Saxby. You've seen it earlier in another talk, so I don't need to explain it in detail. But if you want to write that in Haskell, you would do something like that. You use your higher function, you zip with, then you use a lambda function that takes two parameters, x and y, and return x plus y, and then you have your input ranges. If I want to do that in C++, it's a bit more verbose, but that's just the way it is. But the structure is similar. So your zip with became your transform, and then you have your data ranges. In this case, you have one range and two cursors. And then the last line here is a new concept in C++. It's a lambda functions. So it works almost like a function. You have your parameters here between round brackets. So you have x and y. Auto just means the compiler will deduce the type of them. And then you have a body and a block of code like a normal function. But before the parameter list, you can see A here between square brackets. That's a very important concept called a capture list. It allows lambda functions to use any variable that is accessible from the scope where it's declared. And it has two ways of doing that. Either it creates a copy of it and takes ownership of that copy, or it captures a reference on it, and then you can modify the original object. And we'll come back to that later to see how this is important. So with this kind of structure, we'll see how we can do things like runtime optimizations. So what I mean by runtime optimization is basically compiler optimizations, but at runtime. So to show you an example of these compiler optimizations, that takes matrix multiply. So it's a fairly standard application. It's a bunch of nested loops. So you have to compute for each point of the output matrix, you have to traverse a row and a column of the input matrices. And if you fit that to a compiler as it is, it will generate a control flow graph that looks like that. It's quite complex, you have a lot of packages, a lot of instructions, and so on. However, this algorithm can be heavily optimized if you know the size of your matrix statically. For instance, if you know you have a 2x2 matrix, you can basically unroll everything, and then you just end up with 4 assignments in there. And then the control flow that the compiler can generate from that is much simpler and have far fewer instructions. So C++ compilers are really good at doing that, provided you know the size of your matrix at compile time. But most of the time you don't know it. So C++ doesn't have any mechanism to do this kind of optimization at runtime. So other languages do. For instance, you have Java hotspots and Sorry about that. Right, so you have Java hotspots and V8s that do this profiler-based optimization. So the way they do that is they instrument the code and they build profile traces, and then they analyze these to know candidates of JIT optimizations. However, this is quite unpredictable because these can be nested and they are very hard to find, and we don't know how good the optimization will be in advance. And they're quite expensive because you need to trace everything. And other optimizations try to expose the JIT facilities to the compiler. That's the case to some extent to Array Building Block, and Java Lancet does the same thing. But the problem there is that you ask the programmer to basically solve the problem for you. And very often the programmer doesn't have any clue about these candidates either. And moreover, this approach has an intrusive API where you have to rewrite your code, taking the JIT into account. So the method that we investigated doesn't need any profile information and doesn't need any spatial API. We just use the standard C++ code that I showed earlier. So just the standard IOGA functions with the Lambda functions. And in particular, we're interested in the capture list that I mentioned earlier. So here you have your Lambda again, you have the capture list, your parameters, and the body of the Lambda. But the capture list has some very interesting properties, especially when you capture by value and you create a copy of the objects that you're capturing, because this object cannot be accessed from anywhere else outside the code. So it's a concept of strong ownership. You know by construction that it's accessible. And the syntax provides a very nice way of freezing constants. When you write a Lambda function in C++, it's kind of intuitive which variable should be frozen, should be captured, and which one should be parameters. So the goal here is to change all the Lambda functions in a C++ program into some snippets of self-modifying code to be able to optimize themselves with the runtime values. And the way we did that is by developing a LambdaJIT. So LambdaJIT has two parts. There is an offline compiler that is based on Clang, the C++ 11 compiler. And it performs a set of extra transformations that a normal compiler doesn't do. And in particular, it injects some more data into the binary, which are the output of some static analysis and some internal representation that we'll see in a minute. And this information then gets loaded into a runtime, and then the runtime has a JIT compiler in it, and it's able to recompile the code and to inject these values. So I'll briefly explain how the compiler works. So your traditional C++ compiler are more or less all divided in three parts. You have your front end that converts the input language into some kind of internal representation, or IR. And then you have the middle end that does a bunch of optimization on this IR. And then the back end transforms the IR into some kind of binary. The pipeline we have for the LambdaJIT compiler is slightly more complicated. We do a bunch of transformation in the front end, then we lower that down into IR, and then somehow we manage to pull this IR back into the front end, and then we go through the normal compilation pipeline. And the goal of that is to preserve the IR all the way through the compilation pipeline and to embed it into the runtime, so into the binary, so that the runtime can access it. However, we don't do that for the whole program. Otherwise, we would have the same problem as we did with Java, that we don't know what to specialize at runtime. So, in order to explain what's in there, I'll just explain very briefly the first transformation we do in the front end. I won't have time to explain the entire pipeline. So the first source-to-source transformation we do starts with, for each of our Lambda functions that have the capture list, the parameters, and the body, we transform that into functor objects. So the C++ standard says that any Lambda function can be expressed as a functor object. And the way we do that is the capture list gets promoted into the attributes of a closure type that we generate. Then we generate a constructor that would initialize these values, and then we have a function call operator that has the same type as the return function of the Lambda, then the same parameter as the Lambda and the same body as the Lambda. So that's how Lambda functions are implemented under the hood for most compilers. However, in LambdaJIT, we take an extra step, and we transform the functors into delegates. So it's almost the same. So the grayed out part here is the same as the functor object. However, the difference lies into the function call operator. So instead of executing the computation in the function call operator, what we do is we delegate the computation to an external function that the compiler generates as well. So this call is completely transparent as far as the semantics is concerned. But the interesting thing is that we now have a function that contains the capture list, the parameter, and the body. So this is a completely independent unit of code that does semantically exactly the same thing as the Lambda does. So if we lower this thing in IR, and then we recompile to something different, we can still call it exactly the same way here, but the actual execution will be slightly different. And that's how we select what gets loaded into IR. So for each of these logic functions are then loaded into the runtime, as well as the dependencies, the calling of the functions. And then the runtime can recompile these into optimized code. And then for the higher order function, we go through a dispatcher at runtime, and that's done when the algorithm is triggered and the Lambda function gets invoked. Then the runtime decides how to execute this function, and then it has basically three choices. Either use the precompiled version that is already part of the binary, so this one has almost zero cost. There is already a normal a version of the Lambda in the binary that is precompiled. Or we can choose to recompile the code at runtime and inject runtime values to specialize the code. Or we can decide to delegate this to a computer accelerator. I won't have time to explain in detail all the optimizations that we do in the runtime, but just to give you a flavor of it, we do things like partial specialization, which is the matrix multiply example I showed you earlier. So we can do that at runtime, provided that you capture the size of the matrix, which is exactly how you would write it with Lambda. We developed some neat technique. In particular, we use the IR information in the binary to do things like type introspection that doesn't exist in C++. But we can basically walk through the information in the IR and decompose any user-provided type into a set of primitive type. And then we can decode any pointer on this object. We also developed a specialization compiler cache. So provided a set of runtime values, we can check very quickly whether or not we have a specialized version of this code. So in order to avoid triggering the JIT compilation for the same values over and over again. And finally, we can do things like function composition. So if you call a sequence of lambdas, of lambda functions, we can, in the JIT compiler, we can create a new function from scratch, and then inline all the calls into one newly created function, and do aggressive interprocedural optimization in order to optimize the entire sequence, and then call this unique lambda instead of calling a sequence of functions. The second part is automatic parallelization. I won't go much into detail for that, but the way it works is we have implemented a set of parallel algorithm in the runtime. So it's basically a parallel version of the STL based on the standard C++ 11 threads. And this is combined with the delegates, as I explained earlier, as a potential target for execution. And the way we know that it is safe to parallelize the code is using properties of the Lambda functions. So the compiler is able to check statically whether or not there is a race condition in the Lambda functions. And that's because we can use the concept of strong ownership that I explained earlier. We can use the fact that Lambda functions cannot be accessed from outside. So to show you the corner cases that we're looking at, here we have an integer a, we have a pointer p, and then we have a list of lambdas with different capture sets and different attributes. And for each of those, we need to know whether or not we can instantiate them in parallel. We can invoke them in parallel. So the first one doesn't capture anything, doesn't have any parameters, just do some computation. So this one is obviously safe to parallelize. The other one captured by value, which is by default immutable, so nobody can change this value of it, including the lambda itself. So this one is safe to parallelize. If you capture something by reference, then all the invocation are pointing to the same object. So it's safe to read from it, but obviously if you try to write from it, that's a race condition. And similarly, if you have a pointer or a reference as part of your parameter, you run into some more traditional aliasing problem in C++, and it's very difficult to know statically whether it's safe or not. But as long as you just read from it, you can assume it's safe, but you cannot write to it. And then you have some funny things happening with pointers, because you can capture a pointer by value, in which case you cannot modify the pointer, you can modify the pointee. So in this case, as long as you just read from this pointer, the reference is fine. But if you write to it, then you can't. It's a race condition. And finally, if you have a function foo, well, it depends whether or not you can analyze foo statically or not. And then if you can't, you just assume conservatively the function may not be safe to parallelize. Which brings me to the last part before the evaluation, the dynamic retargeting. So the targets we investigated in this work are GPUs, and they've already been explained in the previous talk, so I won't have to explain in detail why GPUs are good in some cases. But in a nutshell, they have a very, very high performance. So now the latest generation of GPUs are measured in teraflops. So the latest NVIDIA hardware and AMD hardware is around 10 teraflops, compared to 200 to 400 gigaflops for a CPU. And they have very high memory bandwidth. They have hundreds of megabytes per second per thread of memory bandwidth. But the problem is that it's very hard to program for. You need to learn a new programming language. You need to know the architecture well enough. And it's very easy to get things wrong if you don't optimize the memory accesses, if you have divergent code, if your data layout doesn't translate well to GPU, then basically you're not getting anything from it. So instead of doing that, what we propose to do is we can just try out very quickly to translate your code dynamically to the GPU and try to run it on it. And if it doesn't work, we can always backtrack and use the sequential version or the parallel version instead. And it's implemented in the same way the parallel version is implemented. We have an STL version for GPUs, and then we do compiler analysis to know statically whether or not a lambda can be uploaded to the GPU. It's basically the same analysis as the parallel code, but we need to be a bit more careful about pointers and references since it's a distributed memory model. And we need to be more careful about function calls as well. If you call a built-in math function, it's fine, but if you do I/O, if you do anything like that, it cannot run on the GPU. And since everything is based on an LVM, which is what these dragons here mean, we just switch the back end internally, and we can generate PTX very easily. We can also generate things like HSail, cycle, and Spear. So that's all I have time to say about the GPU runtime. So we move on to the evaluation. We implemented 4 different benchmarks with a very wide spectrum of behavior. We have SAXP that was presented at the beginning of the talk, which has a very low compute intensity, doesn't do much. Then we have Black-Scholes, which is an economics application that runs a bunch of values and then output a single value. We have a Monte Carlo method that doesn't read anything, just computes and then write the final result. And we have a factorization application. So we wrote each of these applications in C++ 11. Then we compile that with Clang 03, that's our baseline. And then we recompile the same code with the LambdaJIT compiler. And then we evaluate 3 runtime targets, which are LambdaSec, which is we execute the skeleton sequentially, but we JIT compile the lambda to optimize it. We have LambdaPar, which is we JIT the lambda and we parallelize the code. And we have LambdaGPU, which is we delegate the code to the GPU. So the first application, SAXP, you can see that basically all the target fail to have speed up. So this means that it's not a technique that always works. It's not always safe to parallelize or to delegate to GPU. But the good thing here, 2 good things are, first of all, this one, the baseline is actually achievable with LambdaJIT as well, because we have the precompiled version of the lambda as part of the binary, so we could use that instead. The second thing that's interesting about this graph is the behavior of especially the JITted version. We can see that it does fairly well up to 15 and then crashes again. The reason for that is the A we use in SAXP here is the size of the array as a power of 2. So it's 10, 11, 12, all the way to 23. And the compiler is able to change the multiplication to bit shifts all the way up to 15. And then for some reason, it doesn't apply this for higher power of 2. So then we have a crash in performance. So this shows the sensitivity of this kind of optimization. The second one, Black-Scholes, is an example where we don't really know, it's not really clear which target is best. So we have decent speed up 4 to 6x for all of the execution targets. So if you buy a slightly better GPU, you want to use the GPU. If you want, if you're a slightly better CPU, you want the CPU. So this shows the importance of the ability to switch between targets very quickly. The next one, Monte Carlo, shows one drawback and one advantage of the GPU. The advantage is obviously that for raw computation is much better. So as long as you don't do anything too stupid with the memory, you can get almost 30x on the GPU. However, this curve here shows the impact on communication on these things. So we have to write the data to the GPU, compute, and read it back, which has a cost. So again, depending on your input size, it's important to try out different execution policies. Another thing interesting here is our Lambda GPU actually beats CUDA by 10%, even though they're doing exactly the same thing. And the reason for that is Monte Carlo, this particular application generates random values, and the seed for the random value function is captured. So we can generate a specialized version of the random function at runtime, which the CUDA application doesn't do. The last one shows another drawback of the GPU, which has been discussed already, which is the inability to cope with highly divergent code. So this just shows that the GPU is not always a good idea for parallel applications. So in conclusion, I hope I convinced you that using algorithmic skeletons plus Lambda functions plus a JIT compiler equals better productivity, better performance, and better portability of the code. In terms of future work, some of it will make its way into the standard, not the Z++17, the one after that. That's the parallel version of the STL. There are much more things to be done in terms of functional programming features into the compiler. In particular, lazy evaluation, future, and promises are all in C++11, but the compiler doesn't take advantage of that yet. And there are a lot of low-hanging fruits in the runtime in terms of optimization. We don't do anything clever for optimizing computation, for instance, communication in the GPU. The tasking model we use for the parallel, for parallelizing the CPU version is fairly dumb as well. We don't do anything fancy there. So there's a lot to be done on the runtime, but probably get good, encouraging results from on the preliminary experiments. Thank you.
So, questions for Thibault?
Yeah.
So how much LambdaJIT can do? I mean, basically, you showed the example about matrix multiplication, but you didn't use that in the evaluation, right?
Right.
So it's hard to say whether the LambdaJIT can really kind of, as you said, input the size of the matrix and do this optimization.
Right. So we did actually we didn't include that in the paper, but this optimization is very good on the CPU for that. But the problem is this particular application doesn't translate to the GPU because it uses multidimensional arrays, which don't translate well to the GPU. So I can tell you that on the CPU we got something like, just by using the sequential version but just using the JIT optimization, I think we got about 40% speed up, something like that.
Did you compare with the MTL implementation? Basically, it's the matrix template library.
Right. So this particular optimization, there are a lot of optimization. This particular application, there are a lot of existing optimizations for it. You can do tiling, you can do all sorts of fancy stuff. This was just the naive implementation of matrix multiply, just to show what kind of optimization we do. Any other question?
More questions?
Did you measure the space of the? Sorry, I mean, is there any other?
Yes, please.
Oh. So, which other STL templates can you hook into? So, all your examples were basically map.
Right.
So, is that the only ones that work for the GPU and CPU as well?
So, there is an existing library, a template library in CUDA called Thrust, which basically implements most of the algorithms that the STL does, and they provide CUDA implementation for them, and they use basically anything that you have in Thrust. You can use
So does that require my source program to use thrust? Like I'm just wondering, so the bit of IR that you embed into your executable,
So we
how
use
transportable is that between a CPU version of fold and the GPU version of fold?
for this kind of things, it's where for reducing these kind of things, you just provide the functor, you just provide the binary functor that takes 2 arguments and returns 1.
Yeah.
So this, because you just provide the element function, we can JIT that, we can change the target of that very easily. This because it's not the entire algorithm, so it's not that difficult to translate.
So the IR that you're embedding is it like the LLVM IR?
It's the LLVM IR, yeah. Only for the lambda function.
Yeah.
And then the skeleton is just pre-implemented in the different targets.
Any more questions?
Yes, please.
So sometimes you said that IR contains kind of a lot of information such that you can do type inference or something.
Yeah.
And then you said you only do this selectively. I mean, you don't have all code that have that contain IR.
I can show you very, very quickly on the back of slide. So if you have a bunch of user-defined type like this, in the IR it looks something like that. And then from that you can just build a graph and then go down there and then select whatever you want to propagate. So in this case, if you have an integer, you can propagate that. If you have a pointer, you just skip it because you don't want to specialize the pointer. And then if you have a char, you can specialize it. If you have padding after that, which you might do in structures, you just skip it because you know the align. The align is down there. And that's align 8, so there shouldn't be padding here. But if there is padding, we can skip it. And then we can basically explode any user type into a set of primitives.
So as long as there are no pointers or like reference.
So pointers we just don't specialize against.
Okay.
So if you have a structure that has an int and a pointer, we will specialize against the int, but not against the pointer. So we do partial specialization, it's not full specialization. Yeah.
Sorry. Does this rely in some way on it being a C++ lambda? So I'm just wondering why my anonymous functions are now special compared to named functions.
Right. So the interesting thing about lambda is the capture list. This way, and I'll explain briefly that. So if you just have parameters, they don't really have high optimization potential because you don't really want to cheat a function every time you call it against all the arguments. The capture list of the lambda provide a kind of fixed context. So you kind of know implicitly that you're going to invoke this lambda many times with a bunch of fixed values.
So you can't do this with regular functions. I mean, you can't do this analysis. Like it.
No, you couldn't do it. Well, you could do it, but then you would have to invoke the JIT every time you invoke the function. If that makes sense.
Yes.
Okay, let's thank the speaker again.